Okay, hi everyone, welcome back to this video series on data centers. Spanning Tree Protocol. Spanning Tree Protocol STP achieves its primary objective of preventing network loops on layer 2 network bridges or switches by monitoring the network to track all links and shut down redundant ones. STP uses the spanning tree algorithm STA to first create a topology database and then search out and disable redundant links. With STP running, frames will be forwarded on only premium STP chosen links. Let's take a minute to discuss what we really need STP in more detail. Loop avoidance. Redundant links between switches are good because they help prevent serious network failures if a link stops working. This sounds great, but even though redundant links can be extremely helpful, they often cause more problems than they solve. This is because frames can be flooded down all redundant links, simultaneously creating network loops as well as other evils. Here are the more vile issues redundant links can cause. If there are no loop avoidance strategies in place, the switches will flood broadcasts endlessly throughout the network. This is sometimes referred to as a broadcast storm, but most of the time it's referred to in less printable ways. Figure 12.1 illustrates how a broadcast storm quickly propagates throughout the physical network media. Because the frame can arrive from different segments simultaneously, a device can receive multiple copies of the same frame. Figure 12.2 demonstrates how a whole bunch of frames can arrive from multiple segments at the same time. In the figure, we see the server sending a unicast frame to router C. Since it's a unicast frame, switch A forwards the frame and switch B follows suit. This is bad because it means that router C receives the unicast frame twice, causing unnecessary overhead on the network. You may have thought of this one. The MAC address filter table could become totally confused about the source device's location because the switch can receive the frame from more than one link. Worse than muddled switch could get so caught up in constantly updating the MAC filter table with the source hardware address locations it'll fail to forward a frame. This is called trashing the MAC table. One of the nastiest things that can happen is while multiple loops spread throughout a network, loops occur within other loops. If a broadcast storm happens on top of it all, the network hoses up and can perform frame switching at all. All of these problems must clearly be avoided or at least fixed, and the spanning tree protocol was developed to solve each and every one of them. The spanning tree protocol is key for use in networks like the one shown in figure 12.3. Here you see a switch network with redundant topology that includes switching loops without some of layer 2 mechanism in place to prevent a network loop. The network could be plagued by any of the problems I just talked about: broadcast storms, multiple frame copies, and MAC table trashing. Spanning tree terms. Before I get into describing the details of how STP works within a network, it would be good for you to have some basic ideas and terms down. Root bridge. The root bridge is the bridge with the lowest and therefore best bridge ID. The switches within the STP network elect a root bridge, which becomes a focal point in the network. All other decisions in the network, like which ports should be blocked or put in forwarding mode, are made from the perspective of the root bridge, and once it has been elected, all other bridges must create a single path to it. The port with the best path to the root bridge is called the root port. Non-root bridges. Non-root bridges exchange BPDUs with all other bridges and update the STP topology database on all switches. This prevents loops and helps defend against link failures. BPDU. All switches exchange information to use for the subsequent configuration of the network. Each switch compares the parameters in the bridge protocol data unit BPDU that it sends to one neighbor with the parameters in the BPDU that it receives from other neighbors. Bridge ID. The bridge ID is how STP keeps track of all switches in the network and is determined by a combination of the bridge priority, which is 32768 by default on all Cisco switches, plus the base MAC address. The bridge with the lowest bridge ID becomes a root bridge in the network. Port cost. Port cost determines the best path when multiple links are used between two switches. The cost of a link is determined by the link's bandwidth. Root port. Cost is king when it comes to the root port. It's always the link with the lowest cost path to the root bridge, and do not assume that it will be directly connected. Link between switches, because a gigabit link that passes through two switches to get to the root bridge will be used over a directly connected fast Ethernet link. When non-root switches start up, they must each determine a single path to the root bridge with the lowest cost port becoming the root port. When multiple links connect to the same device and they have the same cost, the port connected to the lowest port number on the upstream switch will be used. The higher the port number will have the discarding rule. Designated port. A designated port is one determined as having the lowest cost to the root bridge via its root port. A designated port will be marked as a forwarding port. All ports on a root bridge are designated port. Non-designated port. A non-designated port is one with a higher cost than the designated port. These are the leftovers after the route and designated ports have been determined. Non-designated ports are put in blocking mode. They are not forwarding ports. Forwarding port. A forwarding port forwards frames and can be either a route or a designated port. Blocking discarding port. A blocked port exists to prevent loops, so it will not forward frames. These ports always listen to BPDU frames but drop any and all other frames to prevent confusion. Make note of the fact that IEEE 802.1d uses blocked ports, whereas 802.1w RSTP uses the discarding rule. Spanning tree operations. Let me summarize here in order to tie descriptions in the previous list together. Basically, STP's job is to find all links in the network and shut down any redundant ones, thereby preventing network loops from occurring. It achieves this by first electing a root bridge that will forward through all ports and act as a point of reference for all other devices within the STP domain. Once all switches agree on who the root bridge is, they must find their one and only root port. Each and every link between two switches must have only one designated port, the port on that link that provides the highest bandwidth toward the route. It's really important to remember that a bridge can go through many other bridges to get to the route, but it's not always the shortest path that will be chosen. Whichever port happens to be the fastest, highest bandwidth will be given that road. Every port on the route bridge is a designated or forwarding port for a segment, because you just can't get any closer to the route without actually being the route. After the dust settles, any port that isn't either a route or designated port will periodically become a non-designated port and put into a blocking state to prevent switching loops. Finally, there can be only one bridge within any given network. I'll discuss the route bridge election process more completely in the next section. Selecting the route bridge. The bridge ID is used to elect the route bridge in the STP domain and to determine the route port for each of the remaining devices when there's more than one potential route port available with equal cost paths. This ID is 8 bytes long and includes both a priority and the MAC address of the device. The default priority on all devices running the IEEE STP version is 32768. To determine the route bridge, the priority of each bridge is combined with its MAC address. If two switches or bridges happen to have the same priority value, the MAC address becomes a tiebreaker for figuring out which one has the lowest and therefore best ID. So basically, if two switches, I'll name them A and B, both use the same default priority of 32768, then the MAC address will be used instead. If switch A's MAC address is 0000.0C00.1111 and the switch's B MAC address is 0000.0C00.2222, then switch A would become the route bridge. Just remember that the lower value is always better one when it comes to electing a route bridge. Prior to the election of the route bridge, BPDUs are sent every 2 seconds out all active ports on a bridge switch by default, and they are received and processed by all bridges. The route bridge is elected based on this information. You can change the bridge's ID by lowering its priority so that it'll become a route bridge automatically. Being able to do this is important in a large switch network because it ensures that the best paths are chosen efficiently is always good. Figure 12.4 illustrates a typical switch network with redundant switch paths. Will determine which switch is the route and then make a non-route bridge become the route by changing the switch's priority. By looking at figure 12.4, you can tell that switch A is the route bridge because it's the one with the lowest bridge ID. Switch B must shut down one of its ports connected to switch A to prevent a switching loop from occurring. Remember that even though switch B won't transmit out that block port, it will still receive BPDUs to determine which port STP will shut down on switch B. It'll first check each link's bandwidth and then shut down the link with the lowest value. Since both links between switch A and switch B are 100 Mbps, STP will typically shut down the higher of the port numbers. In this example, 12 is higher than 11, so port 12 will be put into blocking state. Changing the default priority is the best way to choose the route bridge. This is important because you want the switch closest to the center of your network to be the route bridge, so STP will converge quickly. Okay, now let's make switch B the route in our network via the show spanning tree command. The output from switch B shows the default priority. Switch B config show spanning tree VLAN 0001 spanning tree enabled protocol or STP. Root priority 332769 address 0005.74AE.AE40 cost 19 port 1 Ethernet 3/9 hello time 2 sec max age 20 sec forward delay 15 sec bridge ID priority 32769 priority 32768 sys ID ext1 address 0012.7f52.0280 hello time 2 sec max age 20 sec forward delay 15 sec aging time 300 output cut. There are two things to notice here. Switch B is running the IEEE or STP protocol. The older STP version would read IEEE. Also, the first output or root ID is the root bridge information for the switch network, but it's not switch B. Switch B port, the route port to the root bridge is port 1. The bridge ID is the actual spanning tree bridge ID information for switch B, and for VLAN 1 it's listed as VLAN 0001. Note that each VLAN can have a different route bridge. Switch B's MAC address is listed as well, and you can see that it's different than the root bridge's MAC address. Switch B's priority is 32768. The default for every switch you see listed here as 32769, but the actual VLAN ID is added and called the SYSIDEXT. So in this case it shows up as 32769 for VLAN 1. VLAN 2 would be 32770 and so on. Now let's move on and change switch B's priority using the command shown in bold to change bridge priority on a Nexus switch. Switch B config spanning tree VLAN 1396740484093 VLAN range example 1 357911. Switch B config spanning tree VLAN 1 priority 061440 bridge priority in increments of 4096. Switch B config spanning tree VLAN 1 priority 4096. You can set the priority to any value from 0 through 61440 in increments of 4096. Setting it to 0 means that the switch will always be route as long as it has a lower MAC address than any other switch with its bridge ID also set to 0. If you want to set a switch to be the route bridge for every VLAN in your network, then you have to change the priority for each VLAN, with 0 being the lowest priority you can use. It's never a good idea to set all switches to a priority of 0. Now that we've changed the priority of switch B for VLAN 1 to 4096, we've successfully forced the switch to become the route. Check the output. Switch B config show spanning tree VLAN 0001 spanning tree enabled protocol or STP. Route ID priority 4097 address 0012.7f52.0280. The bridge is the route hello time 2 sec max age 20 sec forward delay 15 sec. Bridge ID priority 4097 priority is 4096 sysidext1 address 0012.7f5 to 0280. Hello time 2 sec, max age 20 sec, forward delay 15 sec, aging time 15, output cut. Both the root MAC address and the bridge priority of switch B are now the same, meaning that switch B is now the route bridge. Knowing the show spanning tree command is very important, and we'll use it again toward the end of the chapter. As you know, you can verify the route bridge with the show spanning tree command, and it is important that you practice and understand the output from this command. However, if you quickly want to find all VLANs for your switch is the route bridge, you can use the show spanning tree summary to get a nice output. Nexus 7K SH spanning tree summary, switch is in rapid PVST mode, route bridge for VLAN 0010, VLAN 0020, VLAN 0030. Port type default is disabled. Each edge port fast BPDU guard default is disabled. Edge port fast BPDU filter is disabled. Bridge assurance is disabled. Loop guard default is disabled. Path cost method is short. STP lite is enabled. Name blocking, listening, learning, forwarding STP active. VLAN 0001 70018, VLAN 0010800008, VLAN 00208 0008, VLAN 003080008, 4 VLANs 3100132 Nexus 7K. By using this command, you can quickly see that this Nexus switch is the route bridge for VLANs 10, 20 and 30. So I'm going to leave it here today for this video. If you like listening, please consider like, sharing and subscribing. Thank you.